My guy. Oops, I recorded that. My bad. Yeah. I don't know. I sometimes I do weird things. So like I said, I don't think this will take too long. We talked about this informally Thursday. So it's 11:21, and we're going to talk about obviously probability. But these are going to be what we call compound events. Yeah, it's actually specifically more than one thing. Yeah. So we call it a compound event when we want more than one thing to happen in succession. So um, for an example of this, you could use, let's say you had some cards. And I don't actually need to draw like the shapes of the cards or whatever. But let's say you had some cards and they had the numbers 1, 2, 3, 4, 5, and 6. And so assume that we have to call them equally likely outcomes. What that means is like none of the cards is more likely to be picked than the other. Like there's not one that has like a jagged edge that your thumb would catch on, or there's no preferential treatment. So you have 6 cards, you have the numbers on these cards, and then you flip them over and just make a pile out of them, right? So any sorts of weird things like that, we'll rule that out. They're all equally likely to happen. So from Thursday, we refreshed ourselves. If I said to you something simple, like what's the probability of drawing a 4? You walked away from Thursday fully confident you understand that notation. The probability of pulling a 4 is exactly 1 out of 6, right? So what we're going to talk about today is the probability of not just a 4, but rather a 4 and then a 5. And so that's a compound event. It's 2 things happening in succession. And there is a question that has to be asked here. And if you're not going to ask it, then I will. But there's a very important question, a bridge that you have to cross before you can answer the math question.
Wouldn't it come back to a half?
It's okay. Let me ask you a question, and I really hope you're paying attention to this because I don't want to go through all this again. This is the question, and I wouldn't expect you to just come up with this on your own, but like if you were doing this in actual practice, yeah, please don't check your email right now. We'll check our emails in 5 or 10 minutes. Okay, so sorry about that. The question. So the question that has to be asked is this, and if you saw yourself doing this in actual practice, so here's the way it would look. I have 6 cards face down. I pick the first one up, and before anyone asks, for these to work, for the problem to make any sense, we always have to assume that the first thing came true. So let's say Luke is sitting here with these 6 cards in front of him, and he picks one up and he goes, jackpot, it's a 4, just like the problem asked. The important question here is this: does Luke take that 4 and set it aside? Or does Luke take the 4 and put it back? And the answer is it could be either or. And that's going to come down to a difference between what we call independent and dependent events. So for the sake of this first example, we're going to say that this is done with replacement. And what that means is that Luke draws a 4. I'm going to say that again. We have to assume that the first one comes true or the problem ceases to exist beyond that point. So Luke draws a 4 and he's like, nice. He takes the 4 and he puts it back in and reshuffles the deck. How many cards are in the deck? There are still 6. And that's really important because as you can imagine, if you do what Cale said, if you take the 4 and you set it aside, sorry to ask dumb questions, but how many cards are in the deck now?
5.
5. And you can see now that that's going to affect the likelihood of him pulling the second card, right? So for our first example, or 2 or 3, we're going to do with replacement. That means that the events are called independent events. You need to know that. Independent means that the one doesn't affect the other. The probabilities are independent of the others having occurred. So here it goes. Let's look at the experiment. If Luke has his 6 cards and they're in a shuffled order and he puts them down and he pulls one, what's the probability that it will come up as a 4? It is exactly 1/6. And then I'm going to put a time sign. If you remember this from Thursday, those of you not writing this down, I would question your motives. I would put a time sign. And this came up, someone had asked a question. It came up on one of your IXL problems. And I thought, it was the 2 coins, wasn't it? Yeah, right. And so what we do is we examine the probability of the first event occurring. And then we put a time sign and we now assess the probability of the second event occurring. So if Luke put the 4 back in the deck, there are still 6 cards in the deck. We agree, right? We talked about that. How many of them are named 5?
1.
And what is 1/6 times 1/6?
1/30.
It is exactly 1/36. So the probability of this compound event occurring, the probability of Luke pulling a 4 and then a 5 is exactly 1/36. If Luke performed this experiment 36 times of pulling a card, putting it back, pulling another card, theoretically, 1 time out of 36, it should be what he wanted it to be.
We should try it.
But the math of it is that it's just a matter of first probability times second probability. That's what it boils down to. And I heard you say some disconcerting things about 12s and stuff. I hope you're past that now. 1 times 1 is 1, and 6 times 6 is, of course, 36, right? Colby brings up an interesting point, and we're not actually going to try this, but if you want to at some point, maybe after break, we can. There's a difference between what we're going to talk about today and what actually happens. That's the difference between theoretical probability and experimental probability. And the simplest example I can give you is this. If you flip a coin 100 times, in a perfect world, how many times would it land on heads? Right. So you would say that theoretically, the probability is exactly 50 out of 100. That's, I call it perfect world probability. Now, if you actually did that experiment, if you grabbed a quarter out of your pocket and flipped it 100 times, would you get 50 heads and 50 tails?
No.
You'd get 59 and 41, or you might get 35 and 65, or you might get 72 and 28. Who knows? But the point is that that's a different field called experimental probability, and we're not going to talk about that. Today's probabilities are what should happen according to the math gods. Just so we're clear. And if you want to try some of these experiments sometime, we certainly can. That's up to you. I need to pause my recording. Do you guys have any questions about that so far? Let's say what question?
Say you pull the 4 out and then you keep the 4 out.
Right. Do you want to try one of those now?
Would it be
5 times
5 times
6.
6?
Yeah, let's take a look at how that changes things. So I wasn't going to segue to that, but your question tells me that perhaps I should. So I'm going to change this now to without replacement. So I'm going to erase the word with and change this to without. These events are no longer independent. I'm guessing you know what they're called.
Dependent.
They're called dependent events. Very good, Brandon. You are a wizard. And so dependent events are where the probability of the second one occurring is affected by the first one having already occurred, right? And so if we do this experiment again, so Luke still wants to pull out 2 cards. He wants to pull out a 4, and then he wants to pull out a 5. But the difference goes back to what Cale said. If he pulls the 4, we assume that he did, he sets it over there. And how many cards are left? And how many of them are named 5? 1. So that changes your second probability. And that's why where the word comes from is we say now that the second probability depends upon the first one. Does that make sense? So he had a 1 in 6 shot at getting his first card, but he has a 1 in 5 shot now of getting his second. So the probability now is better, isn't it? And it makes sense that it would be, because for the second thing to occur, if there's less cards to choose from, then he's got a higher likelihood of getting it, right? And you can work your way on down the line. These compound events, they can go on as long as you want. So like we could make this, and let's keep it without replacement. So let's keep on the dependent events. So we could change it and do a 4 and then a 5 and then an even. That's a triple compound event. So I'm going to need, I'll tell you this, here's a free bit of advice. Yeah, we're still without replacement. Okay, good question. So this is going to be a fraction times a fraction, but new and different times another fraction. And the key to be good at this is just stop and take a snapshot every time you take a step, take a picture. Like, what's the current state of the deck of cards right now? Yes. So my first event we call 4, and the probability of drawing a 4 is exactly 1 out of 6, right? So what you have to do now is take a snapshot of the deck and say, okay, Luke has picked out the 4 and he has set it over there on the table. How many cards are left in the deck? There are 5. So 5 is my bottom number. How many of them are named 5? 1. Good. Now, picture the situation. This is where you got to be, you don't have to write it down, but you got to be kind of a visual enough person to be able to say, what's the current state of affairs? The lay of the land, as they say. How many cards are left in the deck?
4.
There are 4. How many of them are even?
2.
Who are they?
2.
Good for you. Remember, the 4 is out of play. So you got to really understand now in that deck of cards, that little mini deck of cards, the 2 is even, the 6 is even, and that's 2 out of 4, which you could reduce it or you can wait and reduce later. I would reduce now. Do we all agree that 2 out of 4 would reduce to 1 out of 2? So what would overall then the probability be of this happening? 1 out of 60. Very good.
3/4, would it be 3/4?
It actually would be 3 out of 120. So
Yeah.
yes. Yeah, I would always encourage you to reduce everything. But yeah. And by the way, when I reduced, I want to go back in time a little bit and just, I don't know that this would even apply, bless you. I don't know that this would apply to you guys, but you could get creative with your reducing. So like, let's go back to what Sam said. Let's say that this was just, I don't know why it would be, but let's say it was 3 out of 4. Then you see how the 3 fourths can't reduce, right? But this 3 can cross reduce with the 6. You follow? Anything from top floor can reduce anything from bottom floor. And I would always encourage you to reduce early. It's easier. So you could turn this into a 1 and the 6 into a 2. So that's what I wanted to teach you guys today. I don't want to dwell on this any longer. You learn math more when you do it instead of listening to me. So I have 2 IXL skills for you today. They're both over compound events. The first one is going to be pretty easy. The second one is going to be where you start seeing the dependent events, the things that the first one then screws with the second one. Got it? So I'll write the skills. They're not those. Those are from Thursday. I'll write the new skills on the board for you. And that's what you'll be doing today. Good, good.
Yeah.